Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're here to discuss the solutions to problem 3. And this problem has a number of very simple questions that are all related to this classic force versus distance curve that you typically get when you do an atomic force microscope experiment. So basic idea is you've got a force versus distance curve. One of these curves is the approach, the other curve is the retraction. The curve is calibrated in terms of Z. The deflection of the cantilever is just given in volts. This is basically the output from the position-sensitive detector. And these questions are just designed to get you to think about how to analyze a curve like this in some detail. Throughout this problem, we're going to assume that the data was taken with this cantilever with a calibrated spring constant of 0.75 newtons per meter. And the first question just asked, just looking at this curve, it asked you to identify whether the red or the blue curve is the approach, right? So typically the approach starts from some large value of Z. In this case, it's on the order of hundreds of nanometers. You approach the tip to the sample. The tip jumps into the sample at some point. And for this calibration, the jump-in point is at about 50 nanometers. And then you continue to load the tip against the substrate to produce a curve that goes up. The curve stops, right, at some set point force up here, right? So when the position-sensitive detector gives a voltage of 1 volt, the AFM controller reverses and retracts the sample from the tip. When the sample starts to retract from the tip, you follow the blue curve. The tip finally snaps free from the sample, and the force on the cantilever, the deflection of the cantilever is then 0 volts. So this is the basic curve. Clearly, I hope everybody can appreciate that the red curve is the approach, and of the two choices listed in the homework problem, the correct choice would be B. There's also a question about whether this data provides any evidence for any long-range van der Waals interaction forces, right? Long-range van der Waals interaction force would show up as a slight curvature of the cantilever deflection as Z gets smaller, as you approach the tip to the substrate. In this particular diagram, there's no apparent deflection. So I think that the best answer would be no. There's no compelling evidence for long-range interaction forces. Maybe if you looked in more detail here just before the jump to contact, you would see a slight downward deflection of the cantilever, but in this case there doesn't seem to be any strong, compelling evidence based on this data for long-range van der Waals. So I believe the best choice to answer problem or question 2 is B, no. We also asked the question, how is the Z-axis calibrated? In this case, Z equals 0 is set, and that sets the length scale for the Z-axis. How is this calibration arrived at? And the answer is it's often Z equals 0 is often set to equal the point where the cantilever deflection returns to its original value that it had when it was far from the substrate. So when the tip is far from the substrate, the cantilever is not deflected. So Q is equal to 0. The deflection of the bending of the cantilever is equal to 0. When you load the tip against the substrate, you basically reposition the cantilever so that it returns to its equilibrium position when the tip was far from the substrate. right? That's equivalent to this point on the approach curve, and that's how z equals 0 was set. So I think the closest answer to addressing that question is selection C, right? So the first three questions here just are general knowledge questions to make sure that you understand some of the details involved in this cantilever deflection versus displacement experiment. The next three questions require you to go in and make measurements from this graph. I'm not so interested in very careful measurements, so the answers that I provided are roughly order of magnitude numbers, right? So hopefully if you go in and make a measurement, you'll find that there's only one choice that's even remotely close to the correct answer. So I don't expect you to go in and do a very detailed measurement. Most of these can be solved just by inspection. So the fourth question involves the optical sensitivity. In other words, how many nanometers deflection of the cantilever produces 1 volt output from the position-sensitive detector. The way this problem is solved is you have to assume that the data was taken for a hard substrate. If the data was taken for a hard substrate and the statement of the problem claims that to be the case, then if this axis in volts is converted to a deflection in nanometers, then the slope of this curve here has got to equal 1. And the way to make the slope of that curve equal to 1 is to actually measure the slope of this curve and then take the reciprocal of it to define something called the optical sensitivity S. So the slope of the force versus distance curve is basically given by the slope of the red line here. And roughly, you can see that for 1 volt deflection, or for 1 volt signal from the position-sensitive detector, you've gone roughly 50 nanometers, right? So the slope is equal to roughly 1 volt for every 50 nanometers change in Z. And that means that the sensitivity, the optical sensitivity, would then be 50 nanometers per volt, right? So roughly speaking, that's the correct value for this data. And the correct answer for that, of all the choices given, I think the one that's closest is selection D. Once you know that optical sensitivity, then you can start to convert important points on this curve into forces. So for instance, we ask, what is the set point force? That's the maximum force that's applied to the sample. That set point force occurs at 1 volt output from the position sensitive detector. So the set point force is equivalent to a 1 volt signal. But now we have to multiply it by our sensitivity, 50 nanometers per volt, right? And so that tells us the maximum Q, right? So that's the maximum deflection of the cantilever in nanometers, and that's 50 nanometers, right? To convert that deflection into a force, we have to multiply 50 nanometers by our spring constant of 0.75 Newton per meters, right? And when we do that calculation, I think we get about 37.5 nanonewtons, right? So this point here would then correspond to a force of the cantilever on the substrate of about 37 nanonewtons. And I believe the correct answer for that is is C. I think of the choices given, C is the one that's closest. And then lastly, we asked a question about the pull-off force of the cantilever. In other words, how much force is required to pull the cantilever off the substrate? Well, the answer to that question is determined by measuring the voltage that's associated with this pull-off force, which is on the retraction part of the curve, right? We need to know what the cantilever deflection is corresponding to a signal out of the position-sensitive diode of about 2.7 volts, right? So the deflection of the cantilever at this point would be given by this 2.7 volts times our optical sensitivity of 50 nanometers per volt. And when we do that calculation, I think we get about 135 nanometers deflection for the cantilever at this point. Once we know the deflection of the cantilever, we can find the equivalent force. So we just take this 135 nanometers, right? We have to multiply it by the spring constant of 0.75 newtons per meter. Right, and when we do that, I think we get a number, it's about 100 nanonewtons, I think, right? Right, so this point on the curve would then correspond to a pull-off force of 100 nanonewtons. And I think the answer that's closest to that value is B for the choices that are given. So this is a real simple homework problem. It just is trying to give you some confidence that you can work your way through one of these force versus displacement experiments, and then take the numbers that you get from your AFM and then turn them into meaningful values. So that's how I think you solve problem 3.